Welcome and hello. This is a video exercise using the HEC RAS controller. I'm titling this Manning's N calibration. So what we're going to do is calibrate the Manning's N coefficient for the main channel, left overbank, and right overbank. All right, let's go ahead and get started. I'm going to start by going up to File and New Project. Navigate to where you want to save that project. I'm going to put my project right here. I'm going to just call it Project and then click OK. Okay. And then, okay, the unit system is by default US customary. I'm going to switch that right now over to the metric system. So options, unit system, system international, metric system. Okay. Yes. And let's go ahead and build a geometry. So here's the geometric data editor. I'm going to click on river reach. And then we're just going to sketch in the downstream direction, double click, and give our river and reach a name. River A, reach 1. Okay. This is going to be our only river and our only reach, so that makes things simple for the HEC RAS controller. River ID 1, reach ID 1. Next, click on the cross-section editor, and let's go ahead and add a cross-section at river station 0. This is going to be at the downstream end of our reach. I'm going to be pasting in data here for the station and elevation. And then the downstream distance will be 0. The Manning's N, I'm going to start at 0.04 for the overbank and 0.02 for the main channel. The left bank is at 22 meters and the right bank at 49 meters, and apply data. So this right here is a preview of that cross section. Here are the numbers right here. And I'm going to create one more cross section further upstream, 100 meters upstream. So options, and then I'll just copy the current cross section. For the river station, I'll say 100. Okay. And let's see, a few things I need to change here is I'll say 102, 198, because there's a slight bend to the right. I'm going to leave my Manning's N values where they are. In fact, that's probably something worth mentioning. What we're going to be doing in this exercise is determining what are these three Manning N roughness coefficients. I've already assigned them to values, obviously, here, but this is going to be the initial conditions. I'm going to assume that the lowest left overbank Manning's N coefficient is 0.04, the minimum for the main channel is 0.02, and 0.04. And then we're going to incrementally search in the upward direction. So that'll become a little bit more clear what we're doing with the Manning's N coefficient a little bit later in this exercise. All right, so I'm going to apply data, and I need to increase the elevation by, let's add it 0.1 meters, so that'll be a 0.1%. Adjust elevations and 0.1. Okay, apply data and close. All right, so here is our cross section in the map. This is the plan view, and that's all we need to do for the geometry. So I'll go File and Save Geometry Data. We'll call this my base case, so base is fine. Let's go ahead and add some hydraulic data now. We go up to Edit, Steady Flow Data. Now I'm going to start by adding a downstream boundary condition. Click on Normal Depth, and then I said 0.001 is the slope. So, okay, and okay. And then for the flow profiles, I'm going to say 3 separate flow profiles. So say, for instance, we had hypothetical data for 3 separate flow rates and observed water surface elevations, which we're going to be needing a little bit later during the calibration. All right, so those 3 flow rates I'm going to be using is 30 CMS, 350 CMS, and 1100 CMS. All right, so let's go File, and then Save Flow Data. Just call this base as well. Okay, so we can close that. Now let's go ahead and create a plan and run it. So run steady flow analysis. We have the base geometry, the base flow file. Let's go File and Save the plan. I'll just keep calling things base for my base case for now. Subcritical flow regime assumed, and compute. Okay, that's done. Let's close that. Close that. Let's take a look at the cross-section image first. So view, cross-section data. All right. So what we're seeing here is the 3 different flow profiles for this particular cross-section right here. I'm interested in the cross-section downstream. Yep, river station 0. So that's good. DF1 is 30 CMS, 350 CMS, and 1100 CMS for these 3 different water surface elevations. Now, once we increase the Manning's N value as we're searching for our optimal value, we would expect these water surface elevations to increase. Let's go ahead and get the exact numbers here for the water surface elevation. So to do that, I'm going to close that window and then go up to View and then Profile Summary Table. One real thing before I forget, when I was preparing for this exercise, I finally figured out how to toggle on the detailed cross-section data view. So if you're curious where it is, it's not here in the view menu, but if you click on the view menu and you have some results and then click on the letter D, boom, that's how to open it up. At least it does for me for HEC RAS 6.6. So anyway, if you're looking for this report, that's how to access it. But what we want to do is go to the profile summary table. All right, so I'm interested in these bottom three rows because that is River Station 0 for all three profiles, PF1, PF2, and PF3, specifically this column right here. So 201.19, 204.66, and 208.19 are the water surface elevation in meters that were calculated based on all the input data that you saw. Now's a good time to open up Microsoft Excel and show you the table of results and the user interface that I already have set up for this exercise. So what we have here is our range of Manning's n values for the left overbank, the main channel, and the right overbank. A column for minimum and maximum and step. So what we're going to be doing is running a HEC RAS simulation over and over, but what we are going to be changing is these Manning's n values from the minimum value to the maximum value, just doing sort of called a brute force sort of search. But we're going to keep the discretization rather coarse, like 0.02 or 0.01, until we start narrowing down on a specific domain for all three of our decision variables, which happens to be a little bit more accurate based on an error calculation. Okay, so what we're going to do is our first trial, for instance, would be 0.04 for the left overbank, 0.02, and 0.04. And then in these three columns right here for the same row, what I'm going to do is use the HEC RAS controller to not only update Manning's n, run the simulation using those Manning's n values, but also run the simulation and get the results and record the results in these three columns here associated with flow profile 1, 2, and 3 for 30 CMS, 350 CMS, and 1100 CMS. So let me break out that table once again. We're looking at 201.19. So here, 201.19, you can tell that's too low because this right here are going to be the observed values. So 201.19 was below 201.62. Not a problem. That was just our first of many trials. And then the other two numbers are 204.66 and 208.19. 208.19. All right. So what I've done over here in column 11 is calculate an error, which is basically the square root of the sum of the squares between the calculated value and the observed value for all three of our flow rates. That's what's happening in this equation. And then over in column 12, I've calculated a ranking so I can quickly and easily view which of these combinations of n values has the highest rank and hence the lowest error. Okay, that'll make a little bit more sense once we get some more values. We need to, of course, write the VB script that will call the HEC RAS controller and perform all the tasks I described. So what we're going to do is click on the Developer tab and then click on Visual Basic. It'll bring up our Visual Basic here. This is the correct environment. So I'm working in Sheet 1. I've got a couple other Excel files open, but that's fine. This is where I'm going to do my work. First things first, I'm going to paste in the code to open the project. It's going to be passed in a HEC RAS controller object, and then it's going to open up my project.prj using this project underscore open subroutine. All right, and then the next subroutine down, I pasted in. The only other one I've pasted in so far is called update n. What we're going to do is pass it the three n values for the left overbank, the main channel, and the right overbank, as well as a row that we're going to print out those numbers. We're going to create a HEC RAS controller object. We're going to open up that project. And then it looks like if I scroll down here, this is the particular function that we're going to call geometry underscore setman underscore LCHR. This is how we set the Manning's n value for the specific river, reach, and river station in our project. And we're just going to pass in all those variables, the river name, the river reach, the river station number, and then the values that we want it to be updated to, which is the N for left over bank, main channel, right over bank, and then what is this, an empty string here in the event that there is an error. We'll get a message returned. I'm going to be making this update for both cross sections, so river station 100 and 0. And that's all we really have to do. The last thing I'm doing here is saving and quitting HEC RAS, and then also printing out those three N values in columns 3, 4, and 5. So back to the Excel, 3, 4, and 5. I don't need to type that out anymore. That's going to be recorded automatically. In fact, at the very beginning of the main subroutine, which is what we'll look at next, I'm going to start by clearing out all of these results, which reminds me I need to actually add a button to invoke this entire subroutine. So I'm going to go to, how about developer, and then click on the insert button. I'm going to insert a button. I'll just put it right here. And then I don't have a subroutine that I want to call on the button click event yet. So I'll have to come back to that, but I'll just call this run for now. That'll be the label on the button. Let's head back to Visual Basic. Boom. Okay. So scroll down here and then paste in the main subroutine. This is the main subroutine I just pasted in. This is the routine that we're going to assign to that button click event. So we'll have to do that, but let me just explain it first. As I mentioned, we're first going to delete the previous results from row 11 downward. And then after that, we are going to get the data in the user interface for the minimum and maximum values for the Manning's N at the left over bank, main channel, and right over bank, as well as the step value. So everything that's happening right here is just reading in this data so that we know what to loop through a little bit later. All right. Oops. Okay. And then when I say a little bit later, that's happening right here. This first for loop is going to loop through all the Manning's N coefficients for the leftover bank, and then all the Manning's N coefficients for the main channel, and then all the Manning's N coefficients for the right over bank. And then what we're doing with inside each of those loops, each of those combinations of Manning's N roughness coefficients is incrementing the row results. And then we're going to update Manning's N. This is the function that just updates the Manning's N within the geometry file, which we already saw the geometry, and we even already saw this update N subroutine. And then finally, we are going to run the model and record the results. So we're going to call this subroutine called compute record. We're going to pass it the row results, and then we're going to close each of these loops and then finally end the subroutine. That compute record subroutine is what I'm pasting in right now. So that is starting right here. We're passing in the row results. And then let's see, the trial number, I'm just printing that in column 2 of the table. So we'll see the number of trials as they print out. Plus, I'm going to repeatedly print the current trial number in the same cell here. So once it goes out of view, I can still see which trial it's on. All right, we're going to create the HEC RAS controller. We're going to open up the same project as before. In this block of code, we're going to run the steady flow simulation, specifically calling this compute underscore current plan. Then after that, we're going to get the results and print the results using this output underscore node output. I believe that's a function. So before we can call this function, we need to create and prepare the parameters. That's what's happening up here. River ID 1, reach ID 1, node ID, UPDN, profile ID. We're going to loop through 3 separate profile IDs, 1 through 3. And we're also going to be passing the profile ID to extract the results for that specific flow rate. And then let's see, water surface elevation, that's what we're computing here. That's a double. And we're going to round that to the nearest 2 decimal places and ultimately print that on the row results in the column results, which is just going to be, I believe, 7, 8, and 9. Hold on. It is going to be, yes, column 7, 8, and 9 for the columns of our results table. Okay, and then we're going to close HEC RAS. This is just a utility subroutine I built, and I think we're ready to go. So let's go ahead and we need to assign the main subroutine right here as the handler for that button click event. So let's do that. And then let's check our ranges. We'll run the simulation and see what happens. All right, so save this back to Excel. All right, I'm going to right click on the button and assign macro. And this is going to be controller sheet1.main. I've got a few different files open, so I got to be careful which one to click. I think that's good right there. So with this data, 0.04 to 0.06 and a step of 0.02, it's only going to be checking two values, 0.04 and 0.06. If I change the 6, it's only going to be checking two Manning's roughness coefficients for the leftover bank, I should say. So 0.02. However, if I change this to 0.01, then it's going to check 0.04, 0.05, and 0.06. If I change this to 0.005, it's got 5 different values to check for the leftover bank Manning's N. That's 0.04, 0.045, 0.05, 0.055, and 0.06. So I need to make sure that I'm not going to create 1,000 trials because it's going to take a few seconds per trial, which is why I propose our step is extra coarser than helpful, to be honest, but I really just kind of want to see if this is going to run properly. So let's just click on run, and it looks like I've got an error. Oh, yeah. So the HEC RAS controller was not included. This is a critical step if you expect it to work. Tools, references, you want to include the HEC RAS controller libraries. So go ahead and click the checkbox next to HEC River Analysis System. That may not be up at the top of your list. So if that's the case, just scroll down to the H's and boom, HEC River Analysis System. Okay, silly mistake. Let's try this again and hit run, see what happens. Okay. All right, so I'm guessing it's on the first trial now. Yes, we're getting some results, and it's on to trial 2. So what you're seeing in columns 3, 4, and 5 here is the actual Manning's N input values, the roughness coefficients that are used for that trial. And then in columns 7, 8, and 9, these are the water surface elevations in meters, which are calculated results based on the 3 flow profiles of 30 CMS, 350 CMS, and 1100 CMS. Then in column 11, this is the computation for the error that we're calculating based on the difference between that row's 3 calculated water surface elevations and then the observed water surface elevations that are located up here in row 10. Okay, so it looks like it's finished. It has 8 separate trials, a total of 8, 2 to the 3, no surprise there. It looks like our lowest error occurs right here with these 3 water surface elevations, most close to the observed water surface elevations with a rank of 1. Now, as I said, 0.02 is too coarse for us to really get a good feel or have much confidence in that being the best solution. I mean, it is the best solution, but obviously we want higher precision when it comes to our Manning's N roughness coefficient. So I'm going to do this. I'm going to type in 0.01 and then use that as the step for the discretization in our Manning's N roughness coefficient. Click run again and then repeat that same process. But instead of 8 separate trials, it's going to be 27 trials. So we're just going to have to sit back and wait for this to finish. Okay, we're about 16 trials done, 17 trials done. At the moment, this trial number 7 is ranking highest with 0.51 as the minimum error. But we're not done with the results yet, so let's just kind of stand by and see what happens. Okay, that finished up. We now have a total of 27 trials. Here's the bottom trial right here. It looks like our highest ranking trial resulted in an error here of 0.509, 1, 3, and 5. So these 3 scored high, which means these 3 Manning's N coefficients were looking good for us. And then also further up here, 2, 4, and 6. So that is trials 7, 8, and 9. I'm just trying to look at what's similar between the two. So yeah, not a whole lot of conclusions to draw from. It looks like the main channel is either 0.03 or 0.04, so we can rule out 0.02. But then the leftover bank is either 0.04 and 0.06. The right over bank is either 0.04, 0.05, or 0.06, looking at these top 6 ranking trials out of the 27 that we ran. To be honest, that's not quite satisfying for me to want to reduce the range, except for the main channel. Like I said, it's either 0.03 or 0.04. So I'm going to make that reduction right there. And then what I'm going to do is change the step to 0.005 and then 0.05 and 0.05. So that's going to be 5 times 3 times 5, which is 75. So I'm going to go ahead and run that and see how our results change and see if we get a different combination up here of Manning's N coefficients that has an error less than what was our best, 0.509. That's currently our elite combination of values. In fact, let me go ahead and keep track of that. So that's 0.06, 0.03, and 0.06. I'm just going to paste that up here, then type in 0.509. Okay, that's fixed. Let's go ahead and run this again. All right, so I let that simulation run and I wasn't satisfied with the results. So what I did is I dropped the step down even further, down to 0.002. That resulted in a trial of 726 different trials that were calculated with a unique combination of, or a unique permutation of Manning n coefficients. And we calculated the error and have a rank and a final answer. So this computation actually took 45 minutes in case you're curious. So if I scroll down here, what I'm doing is I'm looking for rank 1, which would correspond with the lowest error. So let's just continue scrolling down, looking for single digits. Nothing yet. Okay, so here is 6. 0.014 is much less than what we saw before, but we should have a 1 somewhere in this list. Boom. And this is our optimal solution with a couple neighboring near perfect solutions as well. 0.052, 0.034, and 0.054 for the Manning's n roughness coefficient over the left overbank, the main channel, and the right overbank. That should result in our calculated water surface elevations right here being the same as, let me just copy that to my clipboard right up here. So I'll go ahead and paste the values right there. So 201.62, 206.02, 210.26. Very nice. So that is your final answer. I was actually hiding those same values here just because we go ahead and bring them up. I'll turn them on in blue, 0.0338 and 0.0493. And of course, this is just in the nearest 2 decimal places, so I think that's fine. I felt like the size of this program was enough. Like I said, it took 45 minutes to run. I think I gave a pretty good example of how we can start with a fairly wide range and a large discretization in our search step. And then as we narrow down the domain of possible optimal solutions, we can also reduce the step, run the simulation a number of times, create some sort of error calculation or performance calculation, and then using this rank, we could quickly identify which of our decision variable values were optimal for our calibration.